I must admit I've felt the urge to do some more Vex coding in this one, and when thinking about what could I do to satisfy this urge in Vellum, I stumbled upon Manu's tutorial on connecting the yarns, which back then was done in classic traditional grains. So I thought, why not try and pulling this off in Vellum? So here we go, and similar to our twisty wire setup, we're just going to start off with a grid, set this to YZ plane, scale it to be 1 by 1, and move its center to -1 along the x-axis. And this only needs to have 2 rows and 2 columns, so we end up with one single polygon. Let's drop down a transform sop here and move this over by 2 units, so we'll have those 2 grids facing each other. Now, let's wire in 2 scatter sops here. Let's set each to maybe generate 30 points, one in the original grid and one in the transformed grid. And let's dial in a different global seed and a second scatter here. So we have now points scattered here and points scattered here. Next, as with our twisty wire setup, let's use a point wrangle to generate a few strands here, a few lines. Again, with basically the same code that we then used. First, finding the position of our corresponding point, coming in through a second input slot here, calling it npos, and just looking at it with the point function. Second input slot, we want to look up the attribute p on the point with the same point number as our point we are currently working on. Next, let's create this new point in our first geostream. And finally, create a polyline. Let's check. So yeah, that kind of worked. We're generating our polylines in this weird, chaotic pattern. As these polylines consist only of 2 points each, let's resample those using a resample node and setting its length to 0.0075, like this. So we have now lots of points on those individual lines. Now, if we want to later connect those individual lines with constraints that pull them together, we need some way of finding points that are nearby, but not on the same polyline, so we're not connecting the polyline to itself. And for that, I want to create an individual group for each of those individual polylines here. Let's do that using a point wrangle. And also, before I'm going to start dropping down Vex code in this point wrangle, let me just check that in the resample, I checked curve view attribute, because I'll use the curve view attribute to create a group where I put in the points that will remain pinned, so that will be fixed, basically the endpoints here. Okay, let's do both things. That means fixing the endpoints, putting them in a pin group, and then creating individual groups for each polyline. So we're going to check if our curve view attribute is either equal to 0 or if it's equal to 1, so if it's the first or last point in the polyline, then we'll just set it into the pin group, group_pin. Let's just check if that worked. Yes, 60 points, 30 endpoints here, 30 endpoints here, in the point group pin. Then for creating those individual groups per polyline, let me first create a string, call it grp for group, and it should be equal to a fixed prefix, call it grp underscore for group underscore, and then we'd like to add to this the current prim number. However, to be able to add this and to concatenate this into a string, let's convert this integer attribute here, the primnum, into a string with the help of the function I2a, which will convert an integer to a string. After we've done that, let's just set the current points point group to a string grp, like this. And also, to be able to read out the points group names more easily later, let's just also save a string, call it grp name for group name, and we'll just save the name of the group we just created, which is still stored in this string here that we created, like this. Let's middle mouse on this, so I just created 30 groups, and when I go to the geo spreadsheet, I can see I have my group name set to the individual group here. So that's working. Next, let's finally start creating our Vellum setup, dropping down a Vellum configure constraint, wire this in here, and set the constraint type to string. Just check mass and thickness, and we want to set our thickness to be half of our resample length here, so let's just right click on the length here, go to copy parameter, back into our Vellum constraints, and right click on the thickness, go to paste relative reference, and just multiply this by 0.5. So we'll make sure we have always half of the resample length set into our thickness here. Just to make the simulation a bit more stable later, let's increase the normal and tangent drag by a factor of 10. Let's scroll down here, select our pinpoints, which are in the pin group here, set the pin type to permanent. As we're not moving those endpoints, we can leave match animation unchecked for now, and just increase our bend stiffness to 1 and increase the damping a tiny bit as well to 0.05. Highlight this, so that worked. Now let's drop down a Vellum solver, and before we dive into the solver, let's just attach a null to the constraints here and have a look at my constraint geometry. And you can see there are no point groups in here. While my main geostream has all these point groups here, and they will be transferred to my main vellum stream as well, my constraints are lacking them. So we need to reapply them. We need to retransfer them. I'll just use another point triangle for that, wire in our constraint here and our standard stream in the second input slot here. Delete the null, drop down a bit of vex code. So I'll just read out my string grp, which should be the group name of my points coming in through my second input slot, with the same point number as my constraints point number. Like this. Let's set my constraints points point group accordingly. And also my group name. And for later use in my solver, I want to create two other attributes on those points here. One being an integer, let's call it connections, just storing how many new connections we formed using this individual point. Initialize this to 0, as we don't have any new connections formed yet. And also I want to create an integer array, which I'll call cpts for connected points, in which I'll store the point numbers of those points to which we'll create new connections. And we're going to use this attribute later to make sure that we are not forming multiple connections between the same points. So that's just a list of points. And it's empty for now, as we just initialize it. Okay, that should be it for this wrangle. Let's pipe this back into our vellum solver, and also onto this vellum solver attach two nulls. Call one out underscore geo, with the main geometry stream of that solver. Copy this, put it down. Call this one out underscore for constraints. And this, of course, goes in here. Let's highlight that one. Save this for now, and let's dive into the vellum solver. Before we start working on the vex code inside of this solver, let's just set up our simulation. And I had good experiences with 4 substeps and 8 constraint iterations. And also I dialed back the gravity from minus 9.8 to minus 3. And for now, let's just run this and see what happens. And that's pretty much what we expected, your plain vanilla vellum solver that runs a few strings. Let's reset this and dive into the vellum solver here. As vellum are mainly pops, I'm going to drop down a pop wrangle and use that to do my main vex work. So I want to restrict this onto a group, and want to use an expression in here to make sure that I only apply my code that I'll run to points that have less than 4 connections. So this filters out any points that have 4 or more connections. As I want to be able to kind of dial this in and out direct this a bit, let's just create 2 float sliders first. Call one maxDist for maximum distance. Let's maybe label this max underscore pt underscore dist and create that slider. Pull this down a bit, so that's this one here. Let's maybe set it to 0.3 for now. Just copy this here, paste it again, and rename it to minDist, like this, and also create that slider and set it to 0.05 for now. So this drives the minimum and maximum distance in which we're going to search for points to connect to. Next, let's create a group, because I want to restrict my search to only points that are not in the group as the point from which I'm searching from. So let's get the current points group. That's just a string called grp name, and add in front of it an exclamation mark, so it's negated, and just store this in another string called grp for now. So we just built our own string that excludes the group of the point on which we're currently working. Next, let's finally use this group to look for points close by that are not part of the same polywire. So we're looking for a point number that's an integer. Call this one npt. And we're going to use the nearPoint function, looking on our primary geostream, again using the group string to exclude points which are on the same polywire as the point from which I'm working. I'm going to look from the current point's position, and we're going to look within the max distance. Next, let's get this point's position. And the distance from my currently active point to this found point. Next, let's look up to how many points we've already connected our currently active point by loading our array called cpts. And now let's finally look up if we already connected our currently active point to the near point we just found by checking if we find within our list of points, CPS, if within that list we find NPT, the point number we just found, using the nearPoints function up here. Okay, so far we didn't do that much. We're just basically looking for points close by, getting the nearest point's position, getting the nearest point's distance, and also trying to find that nearest point's point number in our list of points to which we've already connected our point. And now we have everything in place that we need to check if we are actually creating a new connection. So if, and that's going to be a long one. So if we actually found a near point, so that means if our NPT variable is greater or equal than 0, and if our distance d is bigger than our minimum distance, and if we haven't found that point in our list of points to which we're already connected, so that means if the value that this find function returns is smaller than 0, then we can finally create a new constraint between these points. Let's do that by copying over our new point into our current geostream. So a new PT, so we'll add a new point, and use that to create a new primitive, which will serve as our constraint, so a new polyline. Between our current point number and the near point we just found. And I'm realizing I just made a mistake here, so I don't need to copy this point over and newly create it, as it already exists in our geo. So let's get rid of that and just create a primitive between our current point and the found point. Now all we have to do is basically set a few primitive attributes, a few group types, a few groups, and update a few attributes. So let's start with setting all those primitive attributes for our constraint. And those I think will be 5 attributes. So we're going to start by setting a prim attribute on our current geo. Call this one type, which will drive which type of constraint we're creating. We're going to set that on our newly created prim, new prim, and we want to set it to distance. This should be a distance constraint. So let's just copy this, paste it. Next primitive attribute that we're going to set will be the stiffness, and we'll set that to 100 for now. Next one will be the rest length, which will initialize to d, our point distance. Let's just copy this one here, paste it. Next one will be the rest length original, so rest length orig. Set that to the same value as our rest length. And finally our damping ratio, which we're going to set to 0.01. So these are all the primitive attributes that we need for a distance constraint. Later, I'd like those distance constraints to get smaller over time. So I will set those into an individual group, call this contract. So I'll set a primitive group on my first input slot, call this one contract, and add our new prim to it. Now all I have to do is update my point attributes, in which I store the connection numbers and the list of points to which my currently active point is connected. So let's do that by first increasing our connections variable by 1. Scroll down here a bit. And then adding our near point's point number to the list of points to which we are connected by first appending the new point's point number to our list using the push command. So we'll push to our list of connected points our nearest point, and then write out our modified CPS list, the list of connected points, as a point attribute. Like that. Let's just save this, head up one level, make sure we are viewing our out constraints here. Let's enable real-time toggle, keep our fingers crossed, and hit play. And for some reason that did not work as expected, so let's try and find our mistake. And of course I made a mistake in the pop wrangle here, as I didn't check my bindings and I'm still bound to my main geometry, while I would like to execute this on my constraint geometry. So let's change that by just typing in constraint geometry here, capital C, capital G. Again, let's reset this, save this, head up one level, keep our fingers crossed, and hit play. Okay, still nothing. Again, back into our Vellum solver, and this time I think it's the inputs. So I want to set input 1 to myself. Again, let's try this out. Yeah, and now we're generating those additional constraints in here. Let's just zoom in and highlight our prim number display, and making sure that for each point pair connection we're only generating 1 constraint, which seems to work here. Let's reset this, and what I want to do is take care of those constraints that we'll create. They shrink over time. So back into the Vellum solver, and for that we created this new group called contract. So let's use that in a geo-wrangle, which we'll pipe in here. Again, in the data bindings, make sure we are working on our constraint geometry, and then in the code we want to make sure that we only operate on the contract group of primitives. And speaking of primitives, we want to run this over primitives and not points. And all we have to do in here is multiply our rest length by a scaling factor. In our case, let's go with 0.98. And that'll be multiplied each frame. Again, let's save this, keep our fingers crossed and hit play. And that is pretty much doing what I expected. However, there are quite many connections appearing there. So one very naive and simple way of countering this is in our Vellum solver in our pop wrangle, where we decide if we create a new constraint in here, let's add an additional prerequisite and check if a random number, which we're going to generate using the found points point number, is below a certain threshold. So for example, for a probability of 10% of a connection appearing, let's check if it's below 0.1. Again, head up one level and simulate this. So that's exactly behaving as we'd expected, resulting in fewer new connections. So that's how I built a Vellum version of the connecting yarns. Again, a bit heavier on Vex this time, but when we have a look at it, the code basically is lots of administrative stuff, such as setting up primitive attributes and groups, and then is only checking for near points and a bit of distance calculation. With the main work to be done actually in this if expression here, where we're checking that all these conditions are met before we create new connections. So have fun with this, and until next time, it's cheers and goodbye.